Yeah. Now we will look at, let's say I start taking two variables together. This is now where we are entering into the predictions world. The world of predictive analytics or whatever we call as. Let's say here I want to do the relationship between two variables. Like if one is growing, is the other one growing or is it falling? Or vice versa. That kind of analysis I am very much interested in. So for that, from now what I'll do is we'll get into some other interesting data set. Take car sales. It's very interesting data for let's say car sales unprepared. All right. So I'll take this simple data. What it talks of is specific to US, different manufacturers of cars, their different models, and what sales have happened. How many were sold in the last year? Probably you can get it for our country also. All this data, probably if you do some kind of secondary research, all this data can be gathered. So all I am doing, all it is done in this data set is all the cars that are available in the market, all brands, everything. How many were sold in the last year? What was the resale value? And what is the type of that? Is it an automobile or a truck? So probably we can talk about SUVs, LUVs, all this kind of stuff. Then what is its price? And some of the features of the car. Engine power, engine size, horsepower, wheelbase. They are all taken. Fuel capacity, fuel efficiency, some of the factors are taken. Now this data set we'll use for various analysis now. For regression we'll use the same data set. For correlation, for some of the aspects we'll use this data set itself because it is very much apt probably to find relationship between the price and sales, or probably to determine the price based on these features. So for using in the context of correlations and regressions, this data set is very apt to go with. So that's where I would like to use this data set for our next few features discussion. Now, when I say correlation, it is primarily I am trying to find out the relationship between two scale variables. As we have done crosstab analysis as a relationship between two nominal or ordinal variables, the correlation will tell us how strong is the relationship between two scale variables. Why is this needed? If the relationship between two variables is very strong, if someone predicts this variable, the first variable, I can predict the second one easily because I know that the second one moves in some particular way with the first variable. If the first variable is going up, probably the second one also will go up by more or less the same percentage. If that's the case, I don't need to predict the second one. If first one is predicted, I can derive the value for the second one based on the first one. So from that standpoint, correlation becomes a very strong factor. And even if I have to build up my portfolio, this correlation plays a very important role. Some of them are moving in one direction. If they are going up, the others are going down. Probably packaging these two will give me a no profit, no loss behavior. Right? If one is going up and the other one is behaving as if it is going down, or vice versa, packaging these two could result in a no profit, no loss kind of a behavior. So, identifying the correlation, and also I should know, how much strongly are they linked? Because can I use this as an input for determining this? See, today, as a simple example with respect to this. Can I predict my sales based on the price? For that, what should I know? Are these two linked first of all? Right? Historically, I should know, is there any relationship between price and sales? Probably if I ask you theoretically, you may say high priced vehicles, they are not sold more. But my data may prove something else. Or my data might say there is no such relationship. Some high priced vehicles are sold heavily, whereas some low priced vehicles are not even sold much. So our historical, our gut feeling is something different, and what the data is establishing is something different. So my intention always is to understand whether any such kind of relationship exists between the variables or it does not exist. Right? That is the intention of doing a correlation. If that relationship exists, is it strong or weak? If that relationship does not exist, it means probably there is no point in saying price is dependent or sales is dependent on the price, which means sales is dependent on some other factors. To identify your factors which will have an influence on the output, correlation analysis becomes very handy. Right? So trying to find out the interrelationship between the various variables is what is the objective of correlation analysis. Right? So here in this case, I'll try to apply the correlation between the sales and price. These two, though you can do it between any two scale variables, right? I would like to find out what is the relationship between the sales and the price. I'll do it without transforming the data first, and I'll do it after transforming the data. I'll show you the difference between the two, to what extent transformation plays a key role in your analysis, that log transformations and all, because right now we have not transformed the data. We have not even checked for the normality, nothing. Right? Directly, let's say if I apply the correlation between these two, after that check for the normality, remove the outliers, and then apply for the test for normality, and then apply for the correlation. What difference you will get, we can see. Right? All right. What happened? Okay. So initially analyze, then I am going with correlate, bivariate correlation. Correlation between two variables. Partial and all I'll deal with regression. So there is a correlation between two variables. What are the two variables I am looking at? One is the price in thousands and the other one is sales in thousands. These are the two variables between which I want to find out the correlation. Rest all leave it out. These are the things. These are the two variables between which I want to find out the correlation. What is it saying? First of all, I need to see whether the correlation is significant or not. Right? Here, the significance level, whichever is coming out, here are null hypothesis when we go with the correlation, the equality. Right? So the equality is correlation equal to 0, which is no correlation at all. That is the null hypothesis in case of correlation. When I say correlation value equal to 0, it means there is no correlation. If the correlation is equal to 1, it's a perfect positive correlation. Maximum value can be 1. Minimum value can be -1. If the correlation is -1, I am saying perfect negative correlation. If one is going up, the other is definitely going down, and vice versa. Right? If the correlation is around 0, almost no correlation. Null hypothesis is this one. In case of correlation, alternate is it's not equal to. So it is either close to 1 or -1. Right? Either it is positively correlated or negatively correlated. So whenever we are testing for correlations here, the first thing we have to look at is what is the significance level. Instead of looking at the values, first observe the significance level. Is the significance level less than 0.05 or greater than 0.05? If it is less than 0.05, I will go with the alternate hypothesis. Alternate hypothesis is correlation not equal to 0. Correlation, if it is not equal to 0, then we are trying to find out what is it. If it is not equal to 0, we are trying to find out what is it, which is minus 0.30. Right? Minus 0.30 means there is a negative correlation. So if one is going up, the other is going down. If the price is going up, the sales are going down. Right? And because it is not close to -1, the value lies between -1 and +1. The more it is closer to -1, the stronger is the relationship. See, one I am saying there is a negative relation. But the more closer, magnitude wise, the more closer it is to -1, I'll say it's a very strong negative relationship. On the other side, if it is more closer to +1, I say it's a very strong positive relationship. Otherwise, I'll say there is a relationship, but it is weak. A weak negative relationship, minus 0.3. Now, here, let's say, in this case, it is showing minus 0.3. What happens is, when I use this data for my predicting purposes, it assumes that this is the kind of weak correlation that exists between these two elements, and the predictability also, the predictions. See, now what is my intention of doing this analysis? Tomorrow, if I increase the price by 10%, what will happen to my sales? I need to predict my number. Let's say today my price is 1000 rupees. Tomorrow, if I increase it to 1100, what would be the quantity I would be able to sell? Right? That is the intention of doing this analysis. The moment I know this is the price, what will happen to my sales? That's the reason why I am doing this analysis. Now, what is happening here? The relationship is not that strong. There is a relationship, at least I can say. The price plays a key role in deciding the sales. There is a relationship between the two. But there is a weak relation. Probably, let's say, now I can go ahead with this as for the estimation purposes. But when I transform the data, let's say now I transform the data and try to do a similar kind of an analysis. Right? I transform this data, do a similar kind of analysis. First of all, to transform, I need to know whether the existing data is normal or not. So for that, quickly, let's say I am going with the descriptives, where I am looking at sale in 1000 as well as price in thousands. I am trying to find out their skewness and kurtosis. Just quickly repeating the steps which we have done yesterday on this data. Just testing the skewness and kurtosis. See the values, very high. Skewness is 3.4 for this and 1.7 for this. So this data is not normal, but still it has given a correlation of minus 0.3. Right? Now, same thing with the cutoffs is 17 and 3, which are high for both the data, which means both the data are actually not normal. So better transform those data, right? What is the difference in case you don't do the test for normality? How weak is your estimate is what I am going to show. But that's the reason why I have done the correlation before doing the normality. Otherwise, any data we work on, the first thing is test for normality. If it is a scale data, first test it out for normality, then only apply all this. Because the funda of correlations, regressions, t-tests, they all make an assumption that your data is normal in nature. So even when it has done this also, it has assumed that your data was normal. When it has given that 0.3 minus 0.3 as your correlation, it has assumed that your data was normal in nature, whereas in reality it was not. One of the assumptions of the correlation analysis was it assumes that the data is normal. But in reality, your data was not normal because there is a lot of skewness and kurtosis existing on the data. So I am showing probably the difference. See, when I did not do any transformation or any normality check, it has shown that the correlation is minus 0.3. And when you do the estimation part also for the next period, the numbers are taken based on minus 0.3. The estimates are taken based on minus 0.3. Whereas when I do the transformation and bring out the normality and do the correlation, my number could be much different. It could be either close to 0 or it could be close to 0.6, 0.7 also. Minus 0.6, minus 0.7 also, which means there is a strong relationship between the price and the sales, whereas this is showing a weak relationship between the price and the sales. So that's where I am looking at transforming the data. See, here the skewness is coming out as 3.4 and 1.7, where our tolerance limits are plus or minus 0.5. So if it is above that plus or minus 0.5 levels, probably we are saying that the data is skewed. So it is not symmetric. It's not symmetric in the behavior, so it's not normal. If it is not normal, I cannot apply any of our processes like t-tests or correlations. Even if I apply, they are not that strong. I mean, they don't, whatever the output they are giving probably is not a good output to consider. So for that, I should transform the data, make them normal, and if required, eliminate one or two outliers until it becomes normal, and then apply your correlations or everything.
Even before offline transformation, if you remove the outlier and if it becomes normal, then can we outright do it?
Yeah.
Or transformation has to be always done before.
No. If you can remove, see, again it depends on how many outliers you are going to remove. See, as I said, if the skewness is very, very high like this, then removing one or two outliers directly doesn't solve the problem. And that too, when you have inputs like prices, which have a cap on the downward side. When your variables are typically the prices or quantities which have a cap on the downward side, the assumption is they will never follow a normal distribution in their original terms, because there will always be a downside cap. So the price cannot become negative. Whereas if I am talking about growth can, by doing just, I don't need to transform the growth numbers, because there is a possibility of a negative value or there is a possibility of positive value also in that. Then by removing one or two outliers, it may become normal. But these kind of entities, generally the prices, quantities kind of entities, it's very difficult that by themselves they become normal. But yeah, if the skewness is somewhere around 1, plus 1 or minus 1, then you can still assume by removing one or two outliers without doing any transformation, removing one or two outliers, this may come into place. But if the skewness and kurtosis are in the ranges of 3, 4, 10s, the kurtosis is around 17, removing one outlier or two outliers may not solve the purpose. So that is when we are doing the transformation. And because in this case both are variables, sales price, both have a cap on the downward side. They cannot accept negative values. So that's the reason I am initiating with the and sometimes if the transformation is not effective, the skewness will increase even more. Right? If I have done a log transform, let's say right now the skewness is 3.4. If log transform is not appropriate in that case, the skewness will become 5. Which means it is becoming worse. So there is no point in doing a transformation in that case. Better to go with the original itself than remove the outliers. So that's how we are working out. See, sometimes if after I do, probably in this 1 or 2 examples we can look at, after I do a transformation, the skewness may become worse also. If it becomes worse than the original, then it is better off without doing the transformation itself. So I'll take the variable as original rather than the log of that variable. So then with instead of removing the outliers from the log of that variable, I'll remove it from the original variable itself. Or apply a different transform. See, at the end our objective is make it normal. Whatever. So your formula may differ from my formula. But at the end both of our formulas are normal. So that's the intention at the end. Because the more I am bringing it normal, I can apply these correlations, regressions, all these kind of statistical tests and all very effectively.
Will there be any chances of data set not become normal even after
See, in that case, there is nothing much you can predict on those data. See, if I take a completely random set of data, right? I take a completely random set of data. Whatever transformations I do on it, it cannot become a normal. So there are some other patterns which are in a very advanced stages. Either I can look at them as following some extreme distributions, or I'll attribute that entire thing to what a concept called random walk. So the movement is completely random in nature. There is no predictability part in that. Right? If more is random in nature, from here either it can go here or it can go here. There is no way I can predict about the trend of it. So at least generally what happens is some part of it may establish after removing, or sometimes what people do in that is they split the data into 2 parts. 0 to 100 or something as one part, and probably 101 and above as another part. Probably in this part is there a normality. So probably for smaller values there is a normality, but for larger values there is no normality. So it can be sliced and diced to bring out the normality in the data. But if it is not coming, see, why it's not required that I should apply only log or exponent or only these kind of things. I can apply almost any formula on the data. Any big mathematical formulas can be applied, transformation size. So if I apply those kind of transformations, at the end something or the other may crop out. At the end a normality can be established. It's not that I'm only doing log or e power or square root. I can do 100 other formulas. Again they go into mathematical formula. But with some mathematical formula or the other, sine or cos, or with some mathematical formula or the other, I can try to bring in the normality into it. Which means when I take the data from then, I'll take the tan of that data rather than log of that data. Then it becomes normal. Normality can very well be established because the simple funda here is, as we observe large volumes of data, there is a good, if the data is more random in nature, there is a good chance that some transformation on the data will follow a normal distribution. Some transformation, again the transformations I am not limiting myself to only sine or to only log or e power or anything. Probably there could be like e power this plus e power minus this, which is nothing but your sine hx kind of a transformation. Right? Or I can talk about e power x plus e power minus x by e power x minus e power minus x. It could once I do that kind of a transform, probably it is falling into a normal distribution. So that's where my analysis of the patterns. See, in statistics, what we observe is there are almost 40 odd statistical distributions in place. But what we talk of is all these 40 odd distributions which people have, like F, like T, there are 40 odd statistical distributions in place. What is observed is by doing some kind of transformations on those values, they all will become normal. They all can be transformed into normal. So it is that equation. See, when we are saying log transform, it's nothing but the original data is following a distribution called log normal distribution. The prices, if they are not following a normal distribution, here why I am doing a log transform? Because I know the entities like prices, sales and all these things, they follow statistically a distribution called log normal distribution rather than a normal distribution. So which means if I take the logarithm of all those values, they should follow a normal distribution. Like that, there is a statistical distribution called exponential distribution. Right? So by default, the numbers will follow an exponential distribution. But probably if I take the exponent of each of the values, then it will follow a normal distribution. So like that, each data will follow a separate distribution. Now when I do that reverse transformation on that, it will get into a normal distribution. Now, so if I know for this particular data, this is the equation. The reversal of that equation, if I apply a transform on this data, I'll get it as a normal distribution. So, I mean, when we are working on data, people keep applying all kinds of transformation. Removing one or two outliers, I can bring it to normal. If I can't bring it to normal, then it's an issue of a complete random behavior, which means I cannot use any of my techniques to predict. It's completely non-stochastic process. I cannot predict anything on that. Right? Probably if there is a complete random behavior, let's say simple stock markets. If someone says the stock price movement is completely random in nature, then you do any kind of analysis on that, you cannot make money. Probably like a gambling. If I say gambling is completely random in behavior, I cannot make money by doing any kind of analysis on it. I'll make money on a fluke. By doing any kind of analysis on it, I cannot make money. But if I say no, stock market is not like that, if I can understand the patterns in it and try to derive some patterns from it and try to invest in it, and I can make money, then it means it's purely not random. There is some portion in it which can be predictable by applying some kind of transforms or something on the data. I can understand the patterns and based on that do the investing. Whereas if I say it is random, the pattern cannot be repeated at all. Then I cannot predict anything. Even if I predict, something else will happen. Right? So that is where we have to differentiate between the predictability and the statistical tests are being performed for ensuring the predictability levels. If I say that the correlation is very strong between the two, my predictability should become more positive, or I mean I should be able to predict it with more confidence, right? Because for the last 150 records or all cars I have observed, barring one or two or three, let's say if I am able to find very strong relationship between the sales and the price. Now tomorrow any new car is introduced in the market and I know what is its price at, I should be able to predict how much they are going to sell. So as a salesperson, I will predict how many units I can sell this year, at least for setting my own target. That analysis will be useful for me. So the more and more the relationships are established and the statistical relation is being established, we are able to do the prediction with a lot of confidence. And for that purpose, we are doing all this analysis. So even if without transformation, I got some relation. But if I use that relation for forecasting purpose, probably my output can be something else, which may be far away from my reality. Right? My prediction may be far away from the reality. But so I am trying to see, is there any way I can improve on that prediction? For that, first thing I am trying to do is make the data normal. Now once I make the data normal, once we make it, we'll see. I am doing a compute variable.
Why doesn't it show significant factor, right? This 0.00.
No, this is between these two factors, price and sales. Between price and price, the relationship is always 1. The price versus price. Same variable. Same variable, the correlation is always 1 only. I mean, the correlation is always taken with respect to another variable. So here, price versus price, the correlation is 1. So there is no need for any statistical significance, because both of them will always move together only. See, it's as good as taking the price data here, take the price data here. Both will move the same way always. So between same variable, the correlation is always 1. So we are always looking at it with the other variable. With respect to other variable, that significance comes into picture, because those two move in different ways. Right? But the same variable always moves the same. I mean, these guys again, SPSS, they made this in a tabular form. Probably they could have simply made price versus sales correlation. Only this much is sufficient. But they have made the entire thing in a tabular form to make it slightly more confused.
2 points to be analyzed in this table. The first one is what is the significant factor, that is 0.000, and the correlation is minus 0.30.
Minus 0.30. That's it. Right. So there is a negative correlation which is not that strong, which is weaker because of the absolute magnitude. Magnitude is only 0.3, way away from 1, minus 1. So we are saying weaker. So as long as something like 0.6, 0.7, something like that is there, we say it is more stronger. Stronger negative correlation. If it is minus 0.7, I'll say strong negative correlation, or probably 0.6, 0.7 positive, as a strong positive correlation. But otherwise, weak negative, weak positive. But if this significance level is greater than 0.05, I say there is no correlation. Irrespective of whatever the number that is shown in correlation here, I say there is no correlation, because I will go with the null hypothesis, saying correlation equal to 0. Calculation wise, I may still get minus 0.2 or something here, but it is as good as 0. So that's where we first look at the significance level. If it is greater than 0.05, I don't even bother about what is the correlation that is shown there. I'll say it is 0 only. Right? That number that came out is a fluke number. So correlation is 0 only. No relationship between the two variables. But the moment it is less than 0.05, then I'll start looking at the absolute number. And depending on what is that value, I'll say whether it is strong or weak, positive or negative. Now let's say when I do the transformations, I'm doing a computing of two variables only. I'll call it log sales, where I'm using log and I'm inputting sales in thousands. So I'm getting a new variable called log sales. Similarly, I'm computing log price. Two variables I'm computing. This is the input I am giving, log price. So I have two new variables. Now let me try to find out the descriptives not between these two but between the log transformed variables, log sales and log price, which is the skewness and kurtosis I am trying to find out between these two. Now you see minus 0.82, 0.46, 1.5, 0.01. Still there is some level of away from 0.05, which means there could be one or two outliers in both of them. So I am trying to identify the outliers to probably eliminate those one or two records before I do this entire process. Okay, let's assume I am not eliminating the outliers. I am showing in different stages how the correlation is differing. Let's say I am not eliminating the outlier. Now I want to see the correlation between these two variables. Right? We'll eliminate the outliers also and see. But let's say I have not eliminated the outliers. Only transformation done. I am trying to find out the correlation between these two variables. Let's see. Minus 0.51. Negative is becoming stronger, which means my predictability also will become more stronger. Right? There is a strong relationship now compared to the earlier case, which was only minus 0.3. Now it is minus 0.5. So I can very well say that the price and sales are strongly opposite and strongly related. If the price is increased, sales will definitely go down, or vice versa. Right? If the price is decreased, I can increase the sales. That's what history is saying. Of course, there may be exceptions. If they are perfect, probably this number would have been minus 1. If there is a perfect negative, if I increase the price by 10 rupees, sales are down by some extent, then it's a perfect negative where the number will be minus 1. But at least it is minus 0.5, which is showing that in good number of cases, this relationship is holding much stronger. Right? And now, if I go slightly more, even I'll do the elimination of those one or two variables also, or one or two records. So for that we are doing that box plot. Let's say I do the box plot, wherein I am taking for log sales as well as log price, both of them. Here I can label the cases, probably based on model, unique identifier for each record. So I'll put the model as unique identifier. Like which of these models are having stars with respect to this log sales and log price. And probably exclude the cases variable by variable. Do it separately for each of the variables and exclude them. Okay, now when I am doing the box plot, only one star here for log sales. There is one star that is coming out, the model with 3000 GT. That's the model name, which is falling into that star category. So what I can very well do is, which ones were showing values here? For the sales only we had skewness as minus 0.82 and kurtosis is 1.5. Probably for price we are fine. Statistic skewness is 0.46 and kurtosis is 0.01. Both of them are within that plus or minus 0.5 range itself. Whereas for the sales only we are finding something abnormal. And because the skewness is negative, there is some value on the lower side which is an outlier. So that is what is clearly coming out, that 3000 GT is on the lower side which is looking like an outlier. So probably now I'll eliminate this one variable called 3000 GT, right? So for that I am going with select cases. I'll go with the select cases. Instead of all, I'll say the model not equal to 3000 GT, because there is a name that is associated. I'll say select all the cases where the model name is not equal to 3000 GT. So obviously in our data now, if I go back, the 3000 GT should be highlighted or should be crossed off. Look at 84. Mitsubishi 3000 GT is crossed off and rest all models are included. Right? Now let's try out our analysis again. Probably this time I go with the descriptives. Yeah, better. Minus 0.50 is the skewness. Slightly still outside that 0.5 range, but still minus 0.50 is the skewness and 0.31 is the kurtosis. No issues. And even for the price, wow, kurtosis is 0. Almost perfect kurtosis. Right, even though with our data also it has come to very good kurtosis value, and even skewness is 0.46, which is still in the accept. So probably if you want, you can still think of removing one or two more records, or you can stick to it. That's where your analysis versus my analysis will differ. Right, if you are removing one or two more records because 0.50 slightly higher than 0.5, so let me think of removing one or two more records. That record is gone, no? 3000 GT, now that record is eliminated. The record is eliminated. So for that reason, even your kurtosis is also changing. Now, okay, now assuming that this is fine. Now let's look at the relationship. Minus 0.55 almost. Whatever we have started at minus 0.3, it has ended up with minus 0.55. 0.51. Yeah, we got 0.547, right? So 0.03 there was an increase. See, by removing one outlier, we are, see, even this is an increase in, see, it's like instead of minus 0.51, it's as good as saying, probably once we use it in our regression equation, it becomes more and more clear. It's as good as saying my sales equal to, let's say bluntly I am saying this, minus 0.51 times price plus something versus minus 0.54 times price plus something. There's a big difference. Probably your sales prediction may come out completely different. Right? So, I mean, the number, the correlation will actually result in either over predicting or under predicting. Probably in the earlier case there was 0.3. So that could have predicted some other number. Now what is the difference in all these three is how closer we are to the actuals. Right? All these are useful. The relationship first of all is helping me to predict which of them have a strong relation and which of them can be taken as inputs to predict your output. Now earlier it was 0.3 only. Probably that also would have predicted some number. But this is minus 0.54. This is predicting some other number. But what we are saying is this number is more closer to your actual. Probably whatever the actuals come out, based on the experience, this number becomes more closer to the actuals because you will not predict the sales. You will predict the log sales based on this relation. And then reverse it back to find out the actual sales. Right? See, all it is saying is the correlation factor is getting improved, which means the relationship between the two variables is getting more and more improved strongly the moment I am doing a log transform. And once the correlation factor improves, my predictability factor also improves. Right? In the next, when we do the regression, probably we can observe that if I don't transform the data and I do a regression versus transform the data and I do a regression, we can look at our predictions in both the cases. Right? So this correlation helps me in doing this kind of which between which pairs is the relationship very strong, and between which pairs the relationship is not existing at all. Sometimes, okay, someone may say, probably one more example, let's try out. I want to see the relationship. Does the relationship exist between fuel efficiency and price? Right? Highly fuel efficient car, will it be priced more or lesser? Right? I want to check that out. Okay, so price we have already done a log transformation. So at least as far as fuel efficiency is concerned, let me first check whether it requires a transformation or not. So I'll look at the fuel efficiency for its skewness and kurtosis. Skewness is 0.68, kurtosis is 3.2. So probably I may think of either removing one outlier directly or doing a transform. As I said, one side, if I do a transform, if the skewness becomes more worser, then retaining the original itself and removing the outlier makes a lot of sense. And okay, if I do an outlier analysis here, if I get only one or two outliers to be removed, then I can still go ahead removing that outliers directly. But if there are multiple outliers lying in, then it's better to do the transform and then try removing the outlier. Now in this case, let's say if I go with the box plot where I take only the fuel efficiency, you see there is one vehicle called Metro. That is the only one that is becoming a big outlier. Rest all are within the limit. So I don't need to actually transform this data. Only one is outside. But if some, in most of the cases, what we see is there is a big clutter of values lying on the higher side and the lower side. Then what happens is by transformation, all those values will get into the group. Right? Only something which is really outside will go outside. So now what I'll do is I'll eliminate. So as a part of our select cases, I'll write one more rule. If model name is not equal to 3000 GT, how do I write this? And means it takes both, right? Let's try. And model name not equal to Metro. This is what you are saying, right? Let's see. $3,000 GT is eliminated. metro is also eliminated. So I'll put a AND rule saying this not equal to 3000 GT and this not equal to metro. Now when I try repeating the same process, descriptives, I hope fuel efficiency should be fine. Yeah, this is very good. The skewness is minus 0.04 and kurtosis is 0.1, which are very much fine. So now I'll try to pitch in the correlation, let's say between price and fuel efficiency. Where is that? Oh, I did not transform it. No? So I'll take it between the log price and the fuel efficiency itself. Minus 0.57. So this is also clearly telling me that high fuel efficient cars have a less price, right? Or probably low priced cars are highly fuel efficient compared to high priced cars, which might work also, right? If the what is the thing they have used for fuel efficiency? Yeah, miles per gallon. So the higher the miles they are giving means higher is the fuel efficiency. If the fuel efficiency is higher, their price is lesser, and vice versa. Probably we may think the other way also theoretically. High fuel efficiency cars might be priced higher also. But yeah, looking at our Indian surroundings, we can very well say all the low priced cars are the ones which are having the heavy fuel efficiency, right? And similarly, probably I can think of doing some kind of an analysis between sales and fuel efficiency. I mean, are people really looking for high fuel efficient cars or not? Now look at the relationship between these two. Very interesting part.
One is in log domain, another is in actual data. Does it make
Sorry?
one is in log?
Doesn't matter. Two datas, that's it. Two normal datas, normally distributed datas. The most important aspect, significance level, 0.125. Null hypothesis is coming into picture. Null hypothesis is saying correlation is 0. So though you got the correlation as 0.125, you can ignore it. You should not bother about the number here at all. If the significance level is greater than 0.05, that's where I put a two-step evaluation of the correlation. First, look at the significance level. If the significance level is greater than 0.05, your direct conclusion, no correlation. Because null hypothesis comes into picture. Null is correlation equal to 0. Right? Only if that value is less than 0.05, then your alternate comes into picture. Alternate is correlation is not 0. Then how much? For then how much, we will look at the absolute value. But if the significance level is directly greater than 0.05, I should not even bother about the absolute value that is coming up. I am directly saying correlation equal to 0. So there is no relationship between the fuel efficiency and the sales. There is a relationship between price and sales. Now you try to build a relationship curve here. There is a relationship between price and sales, but there is no relationship between fuel efficiency and sales. Right? People are not behind fuel efficient cars only. But even if whatever is the fuel efficiency, if the price is lesser, people are buying it. Right? So, I mean, if you are trying to build up a relation, we are finding that fuel efficient cars are priced lesser. Price, lesser price, higher sales. But the transitive relation is not working out. See here, the fuel efficient car fuel efficient car means low price. Low price means high sales. These relationships are established. But this transitive relationship is not getting established. Bivariate, two. Any correlation is between two variables only. For multiple variables, there is something called partial correlation, where in regression I will bring that out. When I am bringing in regression, I will cover the partial correlation part also. So sometimes this transitive relationships does not occur. So people are more bothered about low price cars, but it necessarily does not translate into fuel efficient cars. Whether it is fuel efficient or not fuel efficient, they are more bothered about a low price car. They are ready to buy a low price car, but they are not specifically focusing on fuel efficient car, which is coming from this analysis. Right? Doing transformation or doing transformation? See, when we are doing this log, I go to this compute variable, just writing one name to it, then the formula, because I am taking a logarithm, I am using a log formula. So from all functions here, I am using the log function. So it gives me log with something in the bracket, and that something I am pointing to, double clicking this one, price in thousands. So a new variable is getting created, which will take the log of the price. So every price item, there is a logarithm that is taken for that, and the values are put in a new column. So here in this new column, this is the actual original price column, but there is a new price column that got created called log price, which is computing for all these prices. For 21.5, the logarithm of 21.5, which is 3.07. Like that they are computed and they are displayed. Now this forms a new field, because this is following that normality. This forms a new field for my next analysis, because this establishes the relation more strongly rather than an untransformed. So that, because I wanted to show the difference between transformed versus untransformed, both of them will give correlation. And once there is a correlation, probably I can put it as a part of my regression prediction also. Now the next analysis which we are going to do is a prediction part into the regression equation. Now if I take the original value, my equation will be different. If I take the log transformed value, my equation will be different. But if I have to look at which one is close to the actuals, it looks like second one would be the more closer to the actuals, because one, the correlation is strong. Two, this entire funda is applied on normal data, not non-normal data. Right? And the assumptions of correlations, regressions and all, they assume that the data is more normally distributed. Right?